Hello, and welcome to Answer Everywhere. Today, we're taking a look at GNU Hurd and GNU Mach. These are the microkernels made by the GNU people before Linux in the hopes of having a kernel for their GNU system, and they've been kind of limping along. Perhaps GNU've heard of them. Get it? Get it? All right, so before we start, I want to do two quick announcemements. One is that we've reached over 10,000 subscribers. Actually, over 11,000 now, but that's what you get when you take too long to do your announcement. They used to send out bronze play buttons, which you can see here. Justin Bieber looks just super excited to have gotten his for 10K subscribers, but they don't do that anymore. Instead, they send me an email. And I'm not joking. The email says that I should share it on Twitter, which also doesn't exist anymore. So I guess they're kind of over the 10K subscriber channels. So that's one. And the other is that recently YouTube sent me my very first check, which is for $108. And I know that a lot of like small businesses, like you go to the laundromat or a small restaurant, will like hang up their first dollar as a symbol of their journey. So I wanted to do something similarly symbolic with my $108. And what I've decided is that I want to create a foundation or endowment for funding open source software. So on this channel, we've been reading the source code of a bunch of different open source projects, and people have asked me about contributing to the projects. I don't have the bandwidth to write code for them, but I thought it would be fun to have a source of money that we can point at different projects and kind of supercharge them based on what we see and what looks cool, and thinking about the ecosystem as a whole as we kind of continue this journey through it. And then you can't just have like an endowment. There needs to be some sort of legal structure. And after thinking about it for a bit, what I've decided is that I'm going to structure it as a church. I'm going to revive the Pythagorean religion. I'm pretty sure that's legal. Let me double check that. Is it legal to start a church in the United States?
Yes, it is legal to start a church in the United States. The First Amendment of the U.S. Constitution guarantees freedom of religion, which includes the right to establish and operate religious organizations. There are certain legal steps.
All right, cool. So the working title is Cult of Pythagoras, which I think is a pretty cool name. Actually, one second. Is it a bad idea to call it a cult?
Yes, it is generally a bad idea to call a religion a cult.
Yeah, so that'll be good. So we'll try that. We'll see how that goes, and I'll let you know when that's all set up. So until then, let's take a look at GNU Hurd. Let's take a quick look at the Wikipedia products for Hurd and Mach. Mach is a microkernel that was developed outside of the GNU people. I think the GNU people have a fork of it. 1985. There are other microkernels that have possibly better properties, including higher performance. I think Cell is one example. Cell 4. High assurance. So this is one of the L4. I guess it's part of an L4 family. And then the problem that microkernels have faced is I think largely performance, but also to some extent complexity. So if you are, the idea of a microkernel is the kernel is as small as possible, and you get out of kernel space quickly and get into user space. And that means lots of inter-process communication. A lot of stuff that would be handled inside the kernel by Linux is handled outside the kernel in a system like GNU Hurd. And so as a result, all of the information there's a lot of information that needs to be transported between the kernel and the user space processes. Hello to the chat. Sweet. Not paying taxes is basically the coolest thing, if I understand correctly from what I read in the news. All right. So let's dig into the host. We are at GNU Savannah. I'm going to try to read it on Emacs. And we're going to start with Hurd. We may need to jump into the Mach code base. All right. So what do we see? We see support for FAT, the FAT file system, the X2 file system. So these are both pretty ancient file systems. FTP-FS. I'm going to guess this is an FTP-based file system. So on things like Linux, we have Fuse, the something user space file system, which is a way to mount things as a file system. And I think in GNU, file system and user space. I think in GNU, lots of things are file systemable. And the line between kernel processes and userland processes gets very weird too quick. That makes a lot of sense. All right, and so I'm not sure what's cool. We'll look at Damon's def pager. That might be important. I don't know. Exec might be important. I guess we could look at one of these file systems. Host mux. Definitely we should look at Hurd. Include an init, I don't know. Login. Yeah, sure, let's look at login. And M4. Let's not look at M4. We have mock def pager, mount NFS, PCI arbiter. Maybe PCI arbiter is important. Proc. Release rump disk. I'm guessing rump is in the sense of like small or, like smallish. And I'm going to guess that maybe that's something to do with startup or bootstrapping with a smaller disk. Store IO and utils. Trans is probably important, assuming that's like some sort of translation layer. And some of these libs are bound to be important, but I'm not sure which ones are. Let's ask I don't know, Gemini. So tell me about the structure of the GNU Hurd code base. What are important pieces of the code base to check out on a first look? All right, so Micr Kernel, we have Hurd servers. Micr Kernel, Hurd servers. Server/directory. The various Hurd servers like file system, libfs, networking. Okay, networking is probably cool because we don't get much user space networking in stock Linux, right? So that's maybe, I guess, not really changing. We're really just pushing the networking into the kernel with ButterFS. But I guess let's look at user space networking. Okay. And how do we want to do this? Let's go to Hurd first. We have lots of defs files. I am going to guess this is some format for defining things. Probably like an IPC sort of mechanism, because that's, I guess, the heart of the Hurd. So we see what I'm going to say when I look at every single IPC or RPC implementation is that it looks roughly familiar from protobufs. So I'm going to guess routine is a function. If you were doing protobufs, this would be like you would have defined a gRPC service. I'm assuming the service is maybe more or less defined by perhaps the file name here, but we have routines, which are like the methods in a gRPC call. And these, I'm going to guess, are arguments to the method. We have this routine ACPI sleep. I forget exactly what ACPI stands for, but it's something to do with power management, I think. But you can ask it to sleep, and you give it a master ACPI type and a sleep state, which can be sleep state 3, sleep state 5. 3 is suspend, 5 is power off. I believe that these numbers are standard. These are not like Hurd decided to start at 3 for suspend. I think S3 is what it's actually called. And then we have this ACPI get PCI IRQ. And we again pass it the ACPI T, which I'm going to which must be some sort of identifier maybe for the kernel ACPI process so that you can do some kind of routing. And then we have a bus and a dev. Presumably bus is maybe where we are going to listen. The dev is some device, I assume. Func is maybe, I don't know, a callback. And out is some IRQ as an int. Get the IRQ for a particular PCI device based on its BDF. BDF must be bus, dev, and function. Okay, so we could look up ACPI, but I'm not going to right now. But let's look at auth.defs. So the subsystem is auth 25,000. 25,000. Okay, should we read this? Definitions for the authentication server. Okay, so 25,000, I don't know, some sort of maybe priority or niceness type thing. Maybe these are used to determine which services come in during like which initialization state. It's probably critical to have something like a file system early on. In fact, let's pull up a file system and see if its number is way earlier. First of all, let's just restrict the defs. I can't get rid of the metadata. No. All right, well, let's try in here. I'm not sure where the file systems are, so never mind. We won't try that. But we have crash, exec, herd types, ifsoc, and interrupt. Let's look at IO controls. So calculate the MIG subsystem that is the first message ID for the RPCs produced by octal requests in the given group. Okay, so whatever this is, we take the group, we subtract F, and we multiply by 4,000 and add to, what is this, 100,000. So this is some number that's larger than auth. I don't know what that means, but these are some numbers. Okay, and so we have some interface, interface. Throughout, the UIDs and GIDs are passed as arrays. One of these arrays is called the effective IDs. These IDs should be used to compute whether a given user is permitted a given operation. The other array is called the available IDs. These should not be used for the computation, for such computation, although they can be turned into effective IDs when calling auth make auth. The first available ID is conventionally called the real ID, and the second the saved ID. Okay, so given an authentication handle, return the identification. So you have some authentication handle. Where you get it, I don't know, but you get these out. You have these out parameters, which are the E UIDs, the A UIDs, and I guess this is the second. These are the the saved ones, and maybe these are the real ones, something like that. Okay, so this is pretty clearly to me some sort of IPC/RPC mechanism. In fact, I think it literally just said that in there. So these are defs. That's what's in Hurd. And we have process and process reply, socket. Should we look at socket defs? Yeah, sure, real quick. This is 1,000 higher than auth. And we can do things like create a socket. So if we want to create a socket, we have to send this IPC or RPC into the kernel and ask it to create a socket with the PFT. I think is just the type. Like, is it, what kind of socket is it? Or rather, I guess that's the sock type. Or, no, the PFT is like the handle, like we saw in auth and the first one we looked at. And you need to tell it what protocol is, and you get some, I guess, which port to send to. I assume is what that's about. And so on for receiving sockets and whatnot. Okay, so those are some IPC definitions. Here's libnetfs. We have some, this is C code now. And we have things like chmod and chown the file, exec the file, make a directory. And these have a relatively nice naming convention. We have Shutdown. Let's look at Shutdown. Let me move the chat off for just a minute. Okay, so Shutdown, we're going to include priv. Priv is maybe privilege or private. Error number, the sysstat. I'm going to guess this is like statistics and not state, but could, I don't know. fsys is probably file system. fs help is probably file system help. We have some args. And just the structure of this looks like we're defining a function of some kind, like an implementation maybe of an RC handler. And we have this helper that's going to return an error type and take in a cookie, a name, and a port, a mock port. We will set the args to be equal to cookie, create an error to turn back, cast the name as a void, and then do what? Call fsys go away, passing in the control thing. This I believe this is likely a handle, given how other things were named with the _t type thing, and passing in the cookie flags. They're called args flags, but they, I guess, came from cookie. And then if we see that MIG server died or mock send invalid destination, then the error is 0, and we return the error. That's a little bit weird. Error 0 usually means, I think, success, but this looks like this actually is probably an error, like the invalid destination. Or maybe we're going to infer that since we're trying to shut down, that's the good result. And then we have NetFS shutdown, which looks roughly similar. We check for some flags. It might be busy, so I guess we send ebusy, which is presumably error busy. There might be some threading stuff. And it looks like we're doing communication of reports. I don't know if this works across the network or if this is just we're using ports for local communication. What else? Let's look at something simple. Let's chmod. So we've got this kernel return type, and we've got netfs s file chmod, and we pass in a prot ID, which is a user, pro TID. I don't know what pro T is. Maybe this is like the user protocol, and we're going to pass in the mode, presumably the mode that we want to change mode to. And if the new user is not existing, then we're going to return the error op not supported. Then we're going to take the mode and AND it with SI format, or if mount is spare and itrans. I don't know what those do. We're ORing those all together and ANDing the mode with the complement of this thing being all ORed together. And then we try to lock something related to the user. We're going to take the user, get a reference, PO, I don't know, NP, I don't know, and lock. So we're going to get this user associated lock. I don't know what PO and NP are in this context. And then we're going to call netfs attempt to chmod, passing in the user PO, NP, and the mode. And then we're going to try to, and then we will unlock and return any errors that we got back from attempting to chmod. I don't see where we passed in the, normally you would change the mode on a file. So I don't know how the file is encoded in this thing. Maybe it somehow is in here. But I think we have enough to now start looking up some stuff. So first, we're seeing some pthread locking. We've seen this NetFS a few times, and we have some sense of what the structure looks like. So let's try mock NetFS. And let's also just try NetFS on its own. NetFS does not exist. Networking through the file system. Stray Alpha. I don't know if this is the same NetFS. It's a file system interface to the networking components of an operating system. It's platform independent and tries to unify existing APIs for easier network configuration. Okay. So this may be the thing. We have NetFS for Linux. What if we try Hurd NetFS? I guess I'll read this later. libNetFS is a Hurd library used for writing translators, providing some virtual directory structures. For example, if you would like to create a translator which shows a .tar archive in an unpacked way, you will definitely want to use libNetFS. However, it is important to understand one thing. Real file system servers like XT3 and such do not use libNetFS. Instead, they rely on libdiskfs, which is generally speaking seriously different from libNetFS. Okay, let's go back to Gemini. And we'll just ask about this code here. The thing I actually really want to know is how do we say what we're chmodding, but we'll see what Gemini says about the code in general. And while it's doing that, let's look for something else to look at. How about demuxer? Can I open this in another window? We have the NetFS demuxer, and we've got a mock message header, which is NP, I guess input, and a mock message header type output. And we've got some routine, and we switch on the routine, really, I guess. Or no, we're not switching because we've got these ORs. Well, if it's any of these things, then we're going to take the input output and call the routine on it, I guess, and then return true. And so this routine must be, I guess, void because it has no return value to note. And then otherwise we're going to return false. So true must be whether we actually called the routine and what routines are supported. Well, we take the input. Okay, so given the input, or this is presumably doing some sort of lookup or computation. So we're like NetFS IO server routine called on imp is going to, I guess, return what the appropriate what the appropriate server routine is for that. And this will short circuit. So if this succeeds, then the routine we're calling is an IO server routine. If this fails, we might call a file system server routine or a notify server routine and so on. Okay. So back to Gemini. The provided code snippet appears to be a function related to manipulating file permissions in a network file system. Here's a breakdown. So user is a structure. I don't know if that's likely true, but that's fine. The mode argument is a bitwise ANDed with a mask to remove unwanted bits. Okay. All right, so we're just clearing bits, I guess. This likely ensures that the new permissions are within the expected range for NetFS, the mutex lock, etc. Okay, so where do we tell it which file we want to chmod on? Okay. So maybe user PO. Yeah, whatever it's called. See if we can go to this. Are there no tags? Did I not compute the tags? Okay, so PerOpen. Maybe PO is something open, something about open, something that's been opened. So we have this prod ID. This library supports client-side network file system implementations. It's analogous to the diskfs library provided for disk-based file systems. So we have port info, the user identification, which is some IO user, PerOpen, object this refers to, and then shared memory IO information, like the shared object and some like mapped memory. And then the PerOpen struct, which is used here, has what? A file pointer, a lock status, some reference counting, open stat, I guess statistics about being open, and a node. So the node is NP. Why P? I have no I have no idea where that P came from. Why not ND? But at any rate, that that seems to be the information about what we're asking to see to change mod on, and that has some lock. Yes, kill it. Okay, so we're getting some information here. Let's get out of NetFS and try our hand at something else. Let's just take a quick look at def pager. We're including mock and some def pager server name, default pager. I don't know if this is for paging memory or something else. You've got some daemon stuff. Default pager, blah, blah, blah. We have this main function. We're going to call it mock task self and get some my task. Then we're going to get privileged ports, which we might fail to do. And we're going to try VM set default memory manager. Which VM? I don't know. Some virtual machine. And we're going to look for whether the -d flag is set, which I guess is the daemon flag. And if it is, we're going to register some like Unix signals, maybe POSIX signals. And we're going to switch on fork. And if we get -1 back, then I guess we can't become a daemon. I guess probably fork returns -1 as an error. If we get 0 back, then I think that we are the parent of the fork. Is that right? I'll look that up in a second. We call set SID with no arguments. We change directory to root, and we close 0, 1, and 2. I'm not sure what is 1 and 2 the standard out and standard error. I'm not sure. And then if we get something other than -1 or 0, then I think that we are the child. And or maybe the thing we get back is the PID. I'll look this up. I forget how fork works. And then we call it sig empty set, and then sig suspend, and then we call exit 0. All right, so let's look at fork. Fork. Not that fork. So the fork shall create a new process. The new process shall be an exact copy of the calling process, except as detailed below. The child process should have a unique process ID. It should not match any active process group ID. Yeah. the return value. Upon successful completion, it will return 0 to the child process and shall not return the process ID of the child process to the parent process. So the one that gets 0 is the child. I got that backwards. Both processes shall continue to execute from the fork function. Otherwise, -1 shall be returned to the parent process. No child process shall be created, and error no shall be set to indicate the error. So 0 to the child process and returns the process ID of the child process to the parent. Okay. Yeah. Okay. So where's our code? Okay. So if we're here, we're the child. And then let's look up close. Oh. Close a file descriptor. So 0, 1, and 2 are the file descriptors. What are file descriptors 0, 1, and 2? Okay, 0 is standard in. I thought 1 was in. So 0 is standard in, 1 is out, and 2 is error. Yeah. Okay, yeah. This has made sense. I forgot about standard in. Okay, so we're closing those things. Why? I don't know, but we are. And then we could panic. Can you set up for me my VS Code? I don't think I can set up your VS Code. I don't even really know what that means. But I have VS Code set up for this machine. I just don't prefer it. Okay, so we have a bunch of stuff left. Login, rump disk, proc. I think I want to now take a look at mock, just to get a feeling for mock. What's it called? GNU mock. We have some debug stuff, some chips, which has buses and buses.c and buses.h. This is mildly modeled after the unibus on Vaxen, one of the most complicated bus structures. Therefore, let's hope this can be done once and for all. Okay, so now we have to know what Vaxen is. Virtual address extension is a series of computers featuring a 32-bit instruction set, blah, 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 blah. It's just some DEC thing introduced in the 1970s. All right. I think we looked up mock very quickly, right? The kernel, I think, is from the 80s, maybe? The original one, 1985. Okay, and so mock has a bunch of stuff, including a kern, an IPC, and IPC implementation in Linux, and a VM. So I guess the VM we saw is probably the mock VM. We have virtual memory. We have Apple. I forgot. Yeah, is that right? So Apple. Where? Here? Is this actually Apple? This is Darwin. I don't know if Darwin is still around. We have some kernel environment with BSD. And this is not what I want. So let's try Apple. Let's try the same search with text instead of images. All right, let's go back. This sounds like this is the place to be. By the mid-1990s, work on microkernel systems was largely stagnant, although the market had generally believed that all modern operating systems would be microkernel based by the 1990s. The primary remaining widespread uses of the Mach kernel are Apple's Mac OS and its sibling iOS, which run atop a heavily modified hybrid Open Software Foundation Mach kernel called XNU. I wonder if that's a play on GNU. In XNU, the file system's networking stack and process and memory management functions are implemented in the kernel. File systems, networking stacks, and process and memory management functions. Okay. So that makes it much more like a macro kernel, right? GNU's mock messages are used for communication between user mode and processes and for some requests from user mode code to the kernel, etc., etc. Okay. I guess let's look at second generation microkernels. Further analysis demonstrated that the IPC performance problem was not as obvious as it seemed. Recall that a single side of a syscall took 20 microseconds under BSD and 114 microseconds in mock running on the same system. So it's nearly an order of magnitude slower. Of the 114, 11 were due to the context switch, identical to BSD. And an additional 18 were used by the MMU, the memory management unit, I think is what that stands for, to map the message between user space and kernel space. So the mapping of like physical memory to like local memory coordinates, I guess, is potentially one way to think of it. That map changes. And so the MMU, I guess, needs to be like reprogrammed to the new coordinate system. This adds up to only 29 microseconds, longer than a traditional syscall, but not by much. The rest, the majority of the actual problem, was due to the kernel performing tasks such as checking the message for port access rights. Okay. So there was some stuff, and then some like optimization and more research. And L4, a series of second generation microkernels, which further reduced the complexity of the system and placed almost all functionality in the user space. For example, the L4 microkernel, blah, 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 blah. Why not build Hurd on L4? Why not build it on Cell 4? Now I want to know about XNU. So XNU, X is not Unix. They totally stole the GNU recursive acronym, developed at Apple Inc. So I guess that they forked, preceded by the Open Software Foundation, which has some microkernel thing. Let's try GNU Hurd L4 microkernel. So it looks like there's some work porting Hurd, or at least people are asking about it. Lost promise. The L4 microkernel. So somehow in the, this is like the, there's some IRC messages. Okay. So the Hurd people know about it, and they have a microkernel page that these are the things that they're working on. There's this PDF on porting it. What year is it? 2003. It's about, what, 11 years ago? We are quoting Plato's Republic, which is the sign that this is probably a good document. And then we have this like wiki page on porting it to a microkernel. And some, whoever this guy is, from 2019. So let's ask ChatGPT, write an impassioned Hurd mailing list message saying we should rewrite GNU Hurd using the L4 microkernel. What sort of style would be good for such a message. A balance of enthusiasm, respect for the audience's expertise, and clear logical arguments. Here are some key elements for such a message. Engage emotionally, historical context, visionary appeal, technical justification, and call to action. All right, dear GNU Hurd community, I write you today with a heart full of passion and a vision for the future. The GNU Hurd project, a cornerstone of our quest, blah, blah, blah. Okay, so rewrite this. Make it much shorter. Assume all mailing list members are not as smart as you, and use the phrase L7 level vision at least twice in the message. All right, that's okay. I'm not going to read it aloud. It's too much stuff. Okay, so back to the code. So it seems like to me it kind of seems like I don't know what they're doing with mock. I guess that I'll have to take a look at what they wrote about the attempts to port it to mock. I'm going to guess it's a combination of things. One of which is that they just don't have a lot of people working on it. So a transition like that would make sense if you had a lot of money and a lot of volunteer effort. May not make sense if you have constrained resources, because you might get like part of the way through a port and never actually finish, or it might take years if you don't have the right resources. So even if the migration made sense technically, it may not make sense organizationally yet, or I don't know if this will ever really be a thing that really gets out the door. I think they have Hurd working. You can like put it on VMs. I don't know if you can realistically run it on bare metal on any machines, but there's a chance, and I don't know, but there's a chance that that there's a technical reason why their version of the mock kernel is really the way to go. And we know that at least Apple seems to be using some version of the mock kernel, although they stuffed all of the outside bits to the inside again. Let's look up, does Apple still use mock kernel in 2024? They may have moved away from it, I don't know. What if we just do Mac OS? The kernel of NextStep is based on the mock kernel. I don't know. Just grepping through stuff, it seems like they're probably still using it, but who knows? Apple kernel is open source too. Cool. I did not know that. All right. And then the other thing Apple uses is BSD, which I think we saw, but I didn't really talk about. Yo. All right, so we have Linux. I don't know what Linux is about. PC MIA, clients, includes modules, wireless. Hermes is some wireless module. Orinoco is some wireless module. I think these are really generic. I don't know if they're tied to a specific piece of hardware. Okay, maybe they are. Hermes 1 is Lucent / Agere, and Spectrum Trilogy chipsets. And then I don't know what Orinoco driver is. Hello. I am in GNOME. Well, I'm in Cinnamon, which is basically a fork of GNOME. Okay. So we've got what appear to be probably Linux modules is what's going on there. We, I guess, have some way to load them. Here's kernel. Kernel has a bunch of stuff. AST will be abstract. What's the word? Abstract syntax tree. ACT. I don't know. something tree, call tree, ACT create. We've got some task and a user stack, and we've got VM stuff. Act, maybe act tree, and we have some act struct and some IPC ports. Let's look at the act struct. Task linkage. So a task's circular list of activations. So act, I'm going to guess, is activation. The activation is only on the task's activation list while active. Must be first. So we've got some queue chain of task links, and then a reference to the task this activation is in, and some machine-dependent state. Consistency, and some act pool. Maybe these are like actors. The activation and act pool hold reference to each other as long as this is non-zero. Some thread linkage stuff. And we have act high or lower. Alert masks, suspend counts, special handlers, and creation stuff. Let's look up mock act kernel. Cool, you're going to make a quantum computer? That sounds fun. You need some what's it called? Super cold stuff. Let's ask Gemini in mock Micr Kernel, what are acts? All right, we've also got threads, tasks, syscalls. Let's look at task, I guess. All right, we have task name size, some reference count, number of references to me, assign active. So I guess maybe act is just like whether the task is running. The task has not been terminated. Some map, address space description. Okay, so we have maybe VM. I've been thinking of it as virtual machine, but maybe it just stands for virtual memory, which would make more sense. And so this is just some virtual memory, I guess, address space description. And then a list of threads. I'm guessing this is like threads we can maybe schedule the task on, the number of threads, and then the processor set for new threads, and some priority for the task, etc. Okay, so this is looking like ordinary tasks. We've got thread stuff, thread swap, timer, XPR, I don't know what that is. Slab, I'm going to guess is slab allocation. Sched should be the scheduler. Do we just have one scheduler? We've got some macro. Thread timer delta takes care of both thread timers. We've got this shift thing. Shift structures for holding update shifts. In valid priority. For fixed priority threads, first quantum indicates whether the context switch at same priority is okay. For time sharing, it indicates whether preempt is okay. Okay, so we're just basically like looking up some stuff by doing some flags, anding and oring. And then we have scheduler routines. We're in the header. So we've got run queue, where we're going to pass it a thread, and I guess it's going to run through the thread's queue or something along those lines. We can choose a thread, passing in, I guess, the processor that's running. And we can get the head of the queue. This is something externally defined. It says assign or shut down queue. And we've got some lock. This is min quantum, presumably the time quantum, max context switch rate. So the minimum time quantum defines the maximum at how fast you can switch. That makes sense? Although it's kind of worded a little bit confusingly. But where's the actual routine? Is it just run queue? Remove a thread from its run queue. The run queue that the process was on is returned. Thread must be locked before calling this routine. Quantum using lasers and crystals. Yeah, that sounds hard. Are you sure that's possible? Okay, so the term ACT, additional communication transport, is not typically used in the context of I don't think this understands what I need. Where was I? So let's see if we can. Wait, I'm having a hard time finding much about the. Maybe what I need is GNU mock instead of just mock. Maybe there's too many mocks. Yeah. All right. So we have thread priority, changing the priority of a thread, handoff scheduling, switching to a new thread, and scheduling policy. And what policies do we have? For thread to policy. So data is policy dependent scheduling. There are two policies, policy timeshare and policy fixed pri. I guess probably fixed priority, etc. And what else? Okay, here, I just read it. So these are the only policies. You can timeshare and fix pri. I'm sure it's not the end of the world to write new ones, but again, there's limited bandwidth, I think, on the GNU Hurd team, so we have limited scheduling. Let's ask Gemini, what are the biggest impediments to getting GNU Hurd into mainstream success? I'm going to guess a lot of it's a ton of stuff, but at the very least, it's also like drivers. I would assume there's probably very, very little hardware support for the current generation of hardware, which is maybe why it needs to run on a VM for the most part. Face several challenges: technically complex, development speed, performance, struggle to match the performance, lack of driver support. This is what I was saying, hardware, and philosophical differences. Of these, the only real, technical complexity is a thing that's kind of like a research project, but it seems like it's doable. Especially there should be enough information from people who work with embedded devices. Development speed, that's obviously a benefit Linux has, but you could imagine a world where there was a dedicated community to Hurd, even if it wasn't like the most popular operating system in the world. And performance is always something you can tune and improve, provided that the IPC mechanism doesn't provide an inherent barrier to performance, which it sounds like in principle it doesn't. But kind of, so I think lack of driver support to me feels like the big thing that's holding it back. Like you can't even get people to install it on like a computer they were about to throw away if it doesn't support the hardware. And so if they can't do that, then it's harder for people to play around with it. And if people can't play around with it, then there's this kind of just bootstrapping problem or a chicken and egg problem where you can't really install it, so people can't hack on it. The reality in human body and nature. To break passwords. Actually, you know what? I don't really know about quantum, how quantum computing intersects with AI. I'm sure there are people working on it. I've thought a little bit and worked a little bit on the intersection of quantum computing with encryption, which has that has a pretty obvious connection given the Grover's algorithm and the other one. What's it called? The more famous one. $1996. Was it Short? Yeah, I think Shor's algorithm is the 1994. Yeah, those things. All right, so back to Mock and Hurd. I don't really know what I want to see other than what we've seen so far. How are we on time? Almost exactly an hour. Let's go back to Hurd, I think, is where I want to be. Should we look at proc? We've got dead name, CPU types, hash, host, info, main. We could look at main. Everything is short. There's not much code, it seems like, for most of these files. Here's the main. I'm not going to read through all of this. This looks like it's mostly initialization, but this is all something you could understand like pretty quickly. This is open console. This is increased priority. Where did main go? Yeah. Okay. There we go. All right, main. So we've got some boot stuff. Mock port. I don't know why boot is a port. There's, I guess, some port associated with boot. We've got an error. A gen port. Maybe that's like general port. Let's open up the reference manual. How about we open it in PDF so that we get it all in one place? So lots of stuff about ports, but is there anything? Here we go, major concepts. The Micr kernel provides message-oriented, capability-based inter-process communication. The IPC primitives efficiently support many different styles of interaction, including remote procedure calls, object-oriented distributed programming. Object-oriented distributed is that like object-oriented in the Smalltalk sense or the Java sense? Because that might just basically be the actor model. Streaming of data and sending very large amounts of data. The IPC primitives operate on 3 abstractions: messages, ports, and port sets. User tasks access all other kernel services and abstractions via the IPC primitives. Okay. They let the task send and receive messages. Tasks send messages to ports. Messages sent to a port are delivered reliably. They may not be lost. That's kind of good to know. I figured it would be more like UPC, but you get some sort of delivery guarantee and are received in the order in which they were sent. It makes use of a VM system. So I guess that sounds like there is actually a VM to efficiently transfer large amounts of data. Or maybe not. I guess VM probably is virtual memory and not virtual machine. And what about, I'm curious if like, how remote is remote procedure call? Like, can the kernel, so in GNU Hurd, can the kernel run on a different machine from some of the user space services? Nice meeting you. All right. All right. They cannot run on different machines. Here's why, et cetera, et cetera. Okay, so sounds like at least Gemini believes that there's not actually remote procedure calls, but I'm not sure. At any rate, back to main. We initialize some stuff. we're going to create a bucket. Ports create bucket. A bucket of what? I'm not sure. Create class 0, 0. Ports create class again. So we have some proc bucket, proc class, and generic port class. And whatever x class. And then creating more ports, creating lots of ports. I guess is a very port heavy thing because we're doing so much IPC/RPC. Then we open the console. And the comment says, get our standard error set up to print on the console in case we have to panic or something. And we have mock port mod revs. Passing in the task self, the auth server, and the port write send, and whatever one is. And then we set some more ports, we deallocate some stuff, add proc to hash, etc., etc. And then this must be the infinite loop, right? While one, ports manage port operations multi-thread. Proc bucket, passing in the proc bucket, passing in the message demuxer. So the demuxer, I'm going to guess all the messages go to the same place, and they have to be fanned out into different users, or at least different user space processes. And then 0, 0, 0 are presumably some like default arguments. So where's the message demuxer defined? Not in here, it seems like. And where is the auth server defined? It seems to be defined. Maybe this is the thing that defines it. Although the variable seems to exist, so maybe there's a main header somewhere. I don't know. Okay. Well, how about we take a look in user mux, and then I might just call it a day here. User mux. We've got some password struct. We've got file numbers, aka inode numbers. For user nodes, these are the UID plus this. I don't know what this is. We have some offset. Oh, I guess this maybe is referring to the offset. And then we have this user mux struct. And we have the names in the that we're muxing between. Some locks. Or rather, I guess one lock for the names variable. A template argz, which is used to start each user-specific translator with the username appropriately added. Okay, so we haven't seen translators, but I think they're a big part of Hurd. And at any rate, so each user, I guess, has their own translator, and they are basically going to get their username appended, which means the usernames have to be unique, which makes sense, but that probably means you can't use this across multiple machines because you can't guarantee unique usernames in an environment like that. And then we have this stuff. What string to replace the trans template with the name of the various user params? If none occur in the template, the user's home dir is appended as an additional argument. So we have user mat, home pat, and UID pat. I guess pat is maybe pattern. But this is basically like string stuff, it looks like. And more templates. And the file that this translator is sitting on top of. Okay, so the user mux struct is mainly the usernames, a lock, and some like helper stuff for templating. It looks like formatting strings to serve each particular user. And then we have the user mux name, the name of a recently looked up user entry. Then we have netnode, the FS specific storage that libnetfs associates with each file system node. And it includes a user mux. The mux this node belongs to. The user can either be the mux root or one of the users served by it. And then we have a name and some trans stuff. And we can create the user node. So let's look back up in the mock documentation. What are they called? Translator? Maybe it's simpler here. A translator is simply a normal program acting as an object server and participating in the Hurd's distributed virtual file system. It's so called because it typically exports a file system, although it need not to, for example, auth, proc, and pfinet, and thus translates object invocations into calls appropriate for the backing store, for example, ext2 file system, NFS server, etc. Object invocations. I don't know what an object invocation is. This is maybe like object-oriented programming, where you have some reference to a thing, and you try to like dispatch it as a method, and then maybe the translator under the hood is responsible for converting it to the proper, actually correct call. Another way of putting it is that it translates from one representation of a data structure into another. For example, from the on-disk ext2 data layout to a traditional file system hierarchy, or from an XML file to a virtual hierarchical manifestation. This translation can be a bidirectional process, but need not be. It's usually registered with a specific file system node by using the settrans command. In mock parlance, a translator is what they name a server, a process that participates in RPC interactions. In the Hurd, a translator is a server that is additionally attached to a file system node. All right, so we've got the file system nodes. They have servers. I assume each server can serve a large number of file system nodes, and they call that a translator. Thus, it is quite common, even in the Hurd context, to speak about servers if you're stressing the RPC part, and on the other hand, about translators if you're stressing the file system part. A translator implements the FS and $IO interfaces. For example, the pfinet server implements the socket API calls, which are mapped by glibc to equivalent RPC calls, compared to a libdiskfs based translator implements a file system based on a backing store. All right, and I want to know what it says about RPC. RPC calls are the basis for just about everything in the Hurd. They're based on mock RPC mechanism. And RPC is made against a mock port, which is the gateway to the translator that will serve the RPC. Okay, but how is this different from IPC? I'm guessing that it just calls IPC using like ports. I think it just calls that RPC. So in Unix, IPC can be achieved using pipes. This is inefficient for large amounts of data, as the data must be copied. Microkernel systems, on the other hand, are generally composed of many components. There is blah, blah, blah. What is the question mark? I guess this is just some sort of search. Respective address space boundaries, unlike the kernel, they cannot arbitrarily examine and modify the caller state. Yeah. Okay. And then there's a link to this IPC article. IPC is done by invoking a port. The two fundamental operations to send and receive messages are used to implement an RPC system. Okay, so it seems like, as I was saying, RPC is basically just what they're calling the mock IPC system. It doesn't actually do like remote procedures, I think, in the sense that it can go over the network. I'm not sure. I see this question here. I was trying to port Emacs C stuffs to Zig using Gemini. It has become really good. That's actually really interesting. Did it work? I'm curious if it worked. All right. Well, while I wait to find out if it worked, I think that I'm going to call it a day there. So that's GNU mock / GNU Hurd. We mostly looked at the Hurd, and then the mock is kind of in the background. We did a quick look at it. I did learn a lot about how it's organized. I will take another look at the documentation, which I think I read long ago. I'm curious to learn more also about are there still enthusiasts who are working on this? If you know someone who's working on it, or if you work on it yourself, I'm curious to hear what's going on. I believe at some point in the past, I installed Hurd on like a VM, and I don't remember anything at all about it, whether I played around with it, whether it runs Emacs. In fact, that's an important question. I guess people are trying to run Geeks on Hurd, and let's see if Emacs will run on Hurd. Download the latest. Yeah. So maybe next time, I don't know. I'll try it out. I'll see if it's worth doing any sort of video on. I'm going to guess that I can't use it as a daily driver, but maybe I can, just for fun. And then maybe, yeah, Emacs version 29.1 runs on Hurd. Cool. All right, so that's GNU Hurd. Hope you enjoyed it. Have a great day, and thanks for watching.